Welcome to a pretty different video. For one thing, I'm facing the wrong way. The camera I usually record with is that one sitting right there. I'm currently recording with my laptop, and the reason I'm doing that is because I want to go and dig into the physics behind my last video. If you haven't seen it, my last video was on the Expanse, surprise surprise, and in particular the motion of a ship in the Expanse, where a person was in the middle of the ship as it circled around them. And I said this was physically impossible. And I was surprised by how many people said that I was wrong. Now, I'm wrong about many things, but in this case, I know my Newtonian physics and I know I wasn't wrong. Which means I didn't explain it clearly enough, so hopefully for those who weren't sure about my explanation, this video will provide some clarity. So it's going to be pretty high level and go through the physics. Hopefully I explain it enough in this, but we will be dealing with a lot of equations, and at the end I'll be showing some plots of what we get from those equations. But the thing I must stress right at the beginning is that this is impossible the way it was shown on the show. You can have a ship fly around in a circle around someone, that's fine, but as it was shown in the show, it was impossible, physically impossible. And the main reason, or the only reason it was physically impossible, was because it didn't meet the conditions for circular motion. Here we have a circle which looks more like an ellipse. But if something moves around in a circle, it must always have a force directed towards the center of the circle. Not some of the time, not once or twice, it always must have a force directed toward the center of the circle. This is the key requirement for circular motion. So why wasn't the Expanse right? Why wasn't this circular motion possible? Well, you get to see my lovely artistic skills. Let's draw the ship. The shape of the ship really doesn't matter. In physics, we distill everything down to the fundamental properties. In this case, you should be lucky I haven't drawn it as a dot. But in this case, actually, the length of the ship actually plays a role in physics. So here we have our ship, and we have the main engine down here. And then up the top of the ship we have another thruster. So here we have the main engine, and this is always on. This is always turned on, and it's always applying a force in that direction toward the center of mass of the ship, which we'll say is there. And then there's the secondary thruster, secondary engine. Apologies for any spelling mistakes. Spelling is definitely not my strong suit. We have at one point there is a force or a thrust that turns on. So this turns on for a few seconds, we'll say. Now, as it turns out, it doesn't actually matter how long it's turned on for. It could be turned on indefinitely, would still get the same result. But the force is turned on for a moment, and this force acts in this direction. So there is a force going that way for a brief moment. And the key point here is that this force isn't aligned with the center of mass, which is this thing here, center of mass. So what that means is that there's a distance between the force and the center of mass, this distance. And in physics, if there is a force displaced from the center of mass, we call that the torque, which is represented by a curly T or a tau, and it's distance times force. And what does a torque do? Well, it changes the rotational motion of an object. So it won't displace it laterally, it will displace it angularly around. So as soon as this thruster fires, the ship will start spinning around the center of mass. It'll start spinning in a circle, alright, but it's spinning around the center of mass. In this case, circular motion is allowed because the ship itself, all of this stuff, is applying a tension force to all of this material to hold it and spin it around in a circle. So that's fine. We have circular motion with the spinning ship. But as with the ship's bulk motion of circling someone else entirely, that's impossible. And we can look at why that's impossible with momentum and forces. So to do it, we need to write down some equations. So we have this equation, F equals ma, force equals mass times acceleration. Now, force is what we call a vector quantity, so I'll put a hat on top of it, and acceleration is a vector quantity. And this just means that it acts in a direction. It has a direction that it's acting, so it has a value or a magnitude and a direction. And the other equation that we'll need is this one here. Change in momentum is equal to force times time. And we also put little vector hats on those ones as well. So we have our two equations that we'll need for now. And now we need to think about what the forces are doing. So, although the ship is sitting in 3D space, we only have two vectors that are doing things. We have one going upward and one going to the side. So that means we can simplify the problem, even though it's sitting in 3D space. We can simplify it by saying that there is a plane that cuts through 3D space that has the directions of our ship and how it's spinning mapped onto it. So what we can end up saying is that force, if we break this apart, force in the y direction is equal to mass times the acceleration in the y direction, or ma as it seems, and f of x, force in the x direction, is equal to mass times the acceleration in the x direction. Okay, so we have those two equations. And as I say, we can do this because we're only dealing with motion in two directions, a plane. Two directions define a plane. We could introduce a third direction, say Fz equals mass times acceleration in z, but we can always find a plane or an orientation where the acceleration of z is equal to 0 in this case. So f of z in these examples will always be 0, so we don't need to worry about it. These are the only equations that we need to worry about for force. So how does the force behave? Well, in the original case, where the ship is just flying upwards, the force behaves, we'll say, entirely in the y direction. So for the initial force, in the initial conditions, we'd have force in the y direction is equal to mass times the acceleration in the y direction, and since there's no acceleration in the x direction, force of x is equal to 0. These conditions don't matter too much because we could say that there's an observer who's in a co-moving frame initially before all of this weird stuff starts kicking in. So we know that this force doesn't stay simple like this because there is a rotation introduced. So how do you describe the force in the x and y direction when you have a rotating thruster? So you have, say, the center of mass here and the ship, and the thruster is firing in this direction at one moment, and then after some time, say it's pointing in this direction, and the thruster is firing this way, so the force is acting that way. You could imagine a whole host of different scenarios, different angles. The ship will rotate around and will fire in all directions. So the net result is you have the center of mass, and you'd have all of the forces, if you looked over time, all of the forces will be pointing radially inward toward the center of mass. So that's fine. We can also describe the x and y components as follows. Force total is equal to, or force total squared is equal to Fy squared plus Fx squared. Okay, so if we were to draw all of this on a plane, what we end up seeing is that on the y-axis and x-axis, initially all of the force is along the y-axis, but after some time the ship spins and now the force is pointing along this direction, and maybe sometime later it'll be pointing along another direction entirely. So that's what we expect to happen. Now you can draw an angle. Any angle will do because we're dealing with pretty simple triangles here, and you find you've got a right angled triangle. And if right angled triangles do anything useful, is that they allow us to do mathematics pretty easily. So we can say that f of y is equal to So this length here is the total force. This length here is the y component. This length here is the x component. So if you know about trigonometry, this solution might be familiar to you. So it would say if total, say sine theta, the angle, and if x is equal to the force total times the cosine of theta. So these forces change as theta changes, which is what you would expect. And they're described by circular motion. But this doesn't mean the ship follows circular motion. So we have equations to tell us how the force acts. And next we want to bring in the other equation we wrote down, which is this momentum equation. So we can say the change in momentum is equal to force times time. Cool. What is momentum? Well, it's change in mass times velocity. In this case, we'll say mass doesn't change, which is probably close enough to being realistic, as is shown on the Expanse. So you'd end up with mass change in velocity is equal to force times time. But what is force? Force is mass times acceleration. So I saw some comments saying that I didn't account for the mass of the ship, and if I accounted for the mass of the ship, it would give a different answer. Well, this equation tells us that's not the case, because you have an m here and an m here, divide both sides by m, you end up with change in velocity is equal to acceleration times time. So the mass of the object makes no difference to the outcome. Okay, so we have time. And in physics you can do things like reparameterization, we call it, to simplify problems. In this case we can do a reparameterization where we set t is equal to 1, or it changes with the same scale as theta. So we'll just evaluate it at each theta step is equal to each time step. That'll matter maybe a little bit later. Okay, so we have then change in velocity is equal to acceleration. Good. So we have an equation, but velocity is a vector component, remember, so this breaks into change in velocity in the x direction is equal to the acceleration in the x direction, and the change in velocity in the y direction is equal to the acceleration in the y direction. Okay. So we also have equations which relate the acceleration to the force, or rather the force to the angle. So we can say that these are equal to mass times acceleration total sine theta, mass acceleration total cosine theta. Okay. Now if you keep those in your mind, we can simplify this equation to be delta v of x is equal to a total cosine theta delta vy is equal to a total sine theta. Okay, so we have our equation which describes how the ship's velocity changes as it spins around its center of mass with the main engine still burning, like we see on the show, which is these equations. So, next we want to think about what is the velocity at any given moment in time. This is just the change in velocity. So the velocity at any given moment in time we'll call vi, and that is equal to the velocity it used to be, so vi minus 1, the last time step, plus the change in velocity. So we would say vxi is equal to vxi minus 1 plus delta vx. Likewise, vyi is equal to vyi minus 1 plus delta vy. Okay, so this tells us what the velocity at each point in time, at each time step, is for Naomi's ship. And we can write these equations down in a programming language. my language of choice is Python. So here is a script here which will do all these calculations for us. I won't go through this in detail. You can look at it in more detail if you want, pause the video. But these two equations are the ones we wrote down for the change in velocity, so we'll define that equation. Here we have our time step, or just the angles. We let it run from 90 or 0 to 360. And we calculate the changes in velocity, so let's plot what they look like. As you would expect, they follow the sinusoids that we gave them. So the velocity changes like the acceleration. So the y velocity is this orange one, which is the sine wave, and the x velocity is the blue line, which changes as a cosine. Good. So next we can do our calculations to work out what the instantaneous velocity at each time step would be by accounting for all previous velocities. So that's done in this for loop here, and we can plot that. And what do we find? They're no longer simple sinusoids. The y direction still looks pretty sinusoidal, but the x direction is always negative. And the reason for that is it's just the initial choice of angle that we decided. So the way that the circle, or the way that the angles started mapping out, went negative first, and then they went positive. So the negative was then cancelled out by the positive, and then went negative again. So it's just a cycle. And this describes an ellipse, which we can see here, where they start off at 0 velocity each, and then when the y value has maximal velocity, the x velocity is going more negative, and then the y value goes to 0 again, and that's when the x velocity is maximal, and then the x velocity decreases, y increases, until y starts decreasing again, and you are back to the same point. In velocity space, this isn't in physical space, this is velocity space. So, this describes to us what the velocity of the ship is doing. Now we can work out what the effect of this velocity has on the ship by calculating the distance. And the distance is calculated by integrating the velocity over time. So the velocity is just the derivative of distance with respect to time. And since we're treating angle as standard for time here, the two are equivalent. So we can do a crude integral by summing components. And what do we get if we plot it? We get this curve here, where you start off at this point, and this is the path an observer would see if they started out as the same velocity as the ship, as if they were co-moving in the beginning. So you can see that the ship increases its y velocity and its x velocity. This is where the y velocity returns to 0, and it's where the x velocity is maximum, and then y velocity goes negative, and x velocity decreases until it's 0 here. The ship is at a standstill, so this is the left side of the ellipse, or sorry, the right side of the ellipse. And then the process repeats over and over. So for each cycle around the ellipse, the net result is that the velocities all end up cancelling each other out momentarily, but the end result is that you've moved in space. So you jump from here to here to here as you cross this path. Now if you were to say spin the ship up faster or spin it slower, then the only result this would have is it would stretch this curve along the x and y axis. It won't change the result. The result will be the same shape. So one person suggested that to Naomi, if she jumped off at any point in this, it would look like circular motion. And you can see that it kind of looks like a sinusoid circular motion, but it really isn't, because it's not symmetric. This jagged point here is not the same as this. In velocity space, the ship is has no velocity, so it sits here momentarily, and then gains velocity and travels off in that direction. This isn't circular motion. This is a strange random path through space. So I need to stress that this is not circular motion. If it were circular motion observed from some distant point, then you would expect to see a sinusoid, not this strange jagged curve. So if you were Naomi and you were jumping off at any point, we can calculate what path you would take by just taking the last velocity value you would have had if you were on the ship. And the reason we do that is because once Naomi leaves the ship, she is no longer being acted on by the ship's thruster, so she no longer has an acceleration acting on her. So if we just pick a random point in time from this curve and see how that behaves, we can do that, and we see this. The ship keeps on its bouncing trajectory, and Naomi rockets off into the distance. She is not bound in this system because she does not have the same acceleration as the ship. She is freely moving, no longer has any acceleration acting on her, no forces, so she'll move at constant velocity at a tangent to whatever strange curve the ship is moving in. There are some special cases though. If she were to jump off when the ship's velocity was 0, then she would more or less sit here as the ship would move away from her. The case where it replicates the show more closely is if she jumped off precisely when the ship no longer had a y velocity but had its maximum x velocity, in which case she would continue in a straight line touching each of these peaks while the rocket would go down here and come back to her. So it would do this strange jagged path, leaving her and then coming back. Not circular motion, but it would be somewhat similar to what they had in the show. And I think it would have been pretty cool as well if they did have this curve in the show, because it would have given the same effect, right? The ship would have been really hard to dock with because it would be spinning quickly, and it would be following this M-shaped path, which many have suggested looks like the McDonald's arch. So the chances of Alex docking with this would be pretty slim. So the circling ship, the ship circling around Naomi, is physically impossible because there is no continuous force directing towards the center of the circle. What would happen is this curve here, and this is what physics tells us will happen. And if you don't believe this, then you're disagreeing with the nature of reality. And I personally would prefer to agree with reality over what I see in a TV show. So hopefully this illuminates the problem a little bit, because it is a pretty complex situation to try and think about. There are lots of moving parts, but as is often the case with physics, if you break it down to the simple components and try and think through what each of those components are doing, you can come to an answer which may surprise you. In this case, it may seem quite contradictory or bizarre that it would follow such a strange line. To be honest, I wasn't expecting it to follow this strange line when I plotted it, but it is what the math tells us is the case. So let me know what you think of this video, if just going into the nuts and bolts of physics is something that you're interested in. And as I said, I hope this explains some of the physics and resolves some confusions that many of you were having. But anyway, thanks for watching, and see you next time.